Today we're going to talk about the Husky electric operated double diaphragm pump. We offer this pump in both a standard AC drive as well as a brushless DC drive with an AC power supply. The electric pump offers lower operating costs and lower pulsation. It also is going to stall like a traditional AODD or air operated double diaphragm pump, which is an advantage over other style electric double diaphragm pumps. We're going to take a look at both the fluid section and the driving section of this double diaphragm pump. Okay, we're going to start by taking a look at the fluid section of this electric double diaphragm pump. In fact, it's actually like a traditional air-operated double diaphragm pump. We have the diaphragm moving in and out of the fluid section, and we have 4 balls and seats. We're going to go ahead and stop the animation, and we're just going to take a look at, again, just the fluid at this point, okay? If you look at what's going on, we have the one diaphragm over here that's being pulled out of the cavity or the fluid cavity, and when it's being pulled out of that cavity, we create a low pressure zone in this area. That low pressure zone allows fluid to fill into the cavity. On the other side, if we're pushing the diaphragm into the fluid cavity, we're actually pressurizing the fluid right here, and that's pushing it up and out, okay? So nothing new here as far as the fluid section from an electric operated double diaphragm pump to an air operated double diaphragm pump. Okay, now we're going to talk about the center section. Let's do some component identification and then we'll talk about what's going on. So first of all, in the center here, you see we have this eccentric cam and roller that's rolling around, and then we have this linear movement carriage, all right? That carriage is connected to the posts that go out to the diaphragms. So what we're going to do now is we're going to stop the animation, and we're going to talk about exactly what's going on here. So first of all, again, I'm going to go back to the eccentric cam with the roller. That's rolling around and it's making contact with the linear carriage, providing that linear movement, all right? When this roller is moving around and it's pulling on this diaphragm right here, it's contacting this pin and it's actually pulling this pin back, which is pulling the diaphragm out of the cavity. On the other side, this diaphragm is supposed to be moving into the cavity, all right? These pins right here are free-floating or sliding within the carriage. So in the center section, as I mentioned earlier, this area right here has a charge, an air charge on it. That charge has to be 10 psi higher than the fluid pressure at the outlet of the pump, okay? So what's happening is this pressure in the center section is actually on the back side of this diaphragm, and it's pushing, it's distributing evenly, pushing this diaphragm into the cavity, all right? This air pressure charge being 10 psi higher than the fluid is very important for both normal operation, batching, and metering, okay? If this is too low of a charge, the pump's gonna stall out. If it's too high of a charge, you're going to produce higher pulsation or fluid pulsation out of the outlet of the pump, okay? Another benefit to having this air charge here is it's going to improve the life expectancy of the diaphragm pump compared to direct drive electric diaphragm pumps, double diaphragm pumps, all right? On direct drive electric double diaphragm pumps, all the force is being pushed right on the pin, and all that force is supported right here, okay? With this air charge, again, we can distribute that force evenly on the back side of the diaphragm, and that's going to give us the improved life expectancy of that diaphragm. Okay, so I mentioned that this electric double diaphragm pump has the ability to stall against pressure, which is a unique function of this electric pump. And I want to talk a little bit about how that's happening. So what's going on in normal operation, the carriage is moving back in a linear fashion and it's pulling the diaphragm back and the air pressure is pushing it back in. But what happens when the fluid gets shut off on the outlet of the pump or a valve gets closed or the demand for the fluid stops, whatever happens, flow stops. And when that happens, fluid pressure in the cavity builds. As soon as fluid pressure exceeds the charged air pressure here, the diaphragms are going to lock in. And remember earlier I said that these little pins right here are kind of free floating through the center carriage. And what's going to happen is once this pressure is bigger than this pressure, the diaphragms lock in, the carriage continues to move back and forth, but it's sliding on these pins right here so the diaphragms can't move. Okay, the last thing we're going to talk about is putting the pump into low pulsation mode and what's going on in the center section. Remember earlier I talked about this section right here, this air charge for standard operating, for batching and metering, has to be set to 10 psi higher than the fluid outlet pressure. For low pulsation mode, you simply want this pressure on the inside or in the center section of the pump to be slightly higher than the fluid outlet pressure. So what's going to happen, we're going to go ahead and stop this operation, and what's going to happen is you're going to see that both pins are now kind of free floating. Because this pressure is only slightly higher than the fluid pressure, what happens is during a changeover or a pump directional change, because these pins are free floating and because this pressure is just slightly higher, both fluid cavities are now energized during a changeover. With both of those fluid cavities energized, we've reduced or minimized or gotten rid of, if it's at the right pressure, any pulsation during that directional change.